Hello, this lecture will do a basic review of digital system design. We will need this information later when we do in chapter 2 when we build a very simple computer. So first let's talk about a few of the basic logic gates. This is an inverter. A 0 on the input produces a digital 1 on the output. A 1 on the input produces a 0 on the output. An AND gate, if you recall, its output is a 1 only if all inputs are 1. An OR gate, the output is a 1 if any input is a 1. An XOR gate you can think of as a binary adder. 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 0. To carry out, we would need to use some additional gating to generate that. And a NAND gate is simply an AND gate with an inverted output. Similarly, a NOR gate is an OR gate with an inverted output. You can implement digital systems by networks of logic gates. You can describe a network of logic gates either by an Boolean equation as done here or in truth table form as done here. This happens to be a majority gate. The output is a 1 if a majority of the inputs are a 1. This is called a two-level form because the first level here consists of AND, the second level is an OR, so this is going to be an AND OR two-level form. This slide shows some Boolean equivalences that arise from something known as De Morgan's law. What De Morgan's law allows us to do is draw some equivalences between AND and OR forms. For example, in this form right here, we have an AND gate with high true inputs and a low true output. That is equivalent to an OR function that has low true inputs and a high true output. This form right here has an OR gate with high true inputs, low true output, and that's equivalent to an AND gate with low true inputs and a high true output. We will find this useful whenever in transforming Boolean networks from an AND OR form to something that only uses NAND logic, as will be shown in the next slide. Using De Morgan's law from the previous slide, we can show that this NAND form right here of the majority gate is equal to the AND OR form that was shown in the previous slide. If you have an AND OR form, you can replace everything with NAND gates and it will implement the same logic function. This will be useful because we'll find out later that NAND gates are actually better in terms of both speed and number of transistors required for implementation rather than using an AND gate. Let's begin talking about actually implementing digital systems. When implementing a digital system, we need to have a physical representing for a logic 0 and a logic 1. In this class, the way that we're going to do that, we're going to use voltages to represent logic 0 and logic 1. The voltage used for logic 1 is going to be whatever our supply voltage is, represented by the symbol VDD. In this class, we will typically use 3.3 volts, even though other systems can use either higher or lower voltages. This particular switch right here, what we want it to do is we want it to output a logic 1 whenever it's pressed, which is this condition here. Whenever the switch is pressed here, we have a short between these two terminals, and this output is going to be directly connected to VDD, so this would be outputting 3.3 volts, which we're going to say is a logic high or a digital 1. This resistor right here, where this there is that when we have a path, when we have this direct connection to VDD, we will also have a current path from ground to VDD, and all this resistor does is limit the amount of current that flows in this path. By the way, ground represents logic 0 volts. So whenever the switch is open, there's no path here. This is essentially an infinite resistance. It's open, so the actual voltage level in this signal is going to be 0 volts. So when the switch is not pressed, we have a 0 volt signal, which is going to equal to a logic 0. When the push button is pressed, we're going to be outputting 3.3 volts to this line right here, which we're going to call a logic 1. This is actually a more commonly used push button configuration for outputting logic 0, logic 1. And this is one that we're going to use in this class. In this particular case, it's called a low true switch. When the push button is open, then that means we have a path here to VDD. We're not shorting it to ground. So this would be high, which means that when the push button is open, not pressed, we're going to have a logic 1 out. When the push button is pressed, then, or we'll call it asserted, then we're going to have here 0 volts out, which we're going to end up calling logic 0. Let's talk about creating logic gates. To create a logic gate, we need transistors. And the most common transistor technology today used for creating logic gates is called CMOS, which stands for complementary metal oxide semiconductor transistors. There are two types of these. There are P and N, and they're complementary operations to each other, which means that they operate in opposite conditions to each other. Let's talk about, first of all, what's called an NMOS transistor. There are three terminals, a source, a drain, and a gate. We're going to view these things as simply as simple switches. Whenever the gate is a 0, then that means that the switch is open. There's no current flow between the source and the gate. When the gate is a logic 1, it means the switch is closed. It means we're going to have current flow between G and D. For a PMOS transistor, it's exactly the opposite behavior as denoted by this inverting bubble on the gate. When the gate value is a logic 0, it's closed. When the gate value is a logic 1, the switch is open. The simplest type of logic gate that we can build is an inverter, and an inverter takes exactly two CMOS transistors, one PMOS and one NMOS, where the PMOS is connected to VDD and the NMOS is connected to ground. When viewing these things as switches, when the input is a 1, this switch, the NMOS, is closed, and this switch, the PMOS, is open, which means that if this switch is closed, the output's being pulled to ground and we get a logic 0 out. We want to make sure that both of these paths cannot both be closed at the same time, because if they were, then we'd have a short excessive current flow between VD and ground. Whenever A is a 0, the opposite is occurring. This switch right here is closed. This switch right here is open, which means that the output is being pulled up to VDD, which will be a logic 1. In order to build a non-inverting logic function, we need two stages of inverting CMOS logic. So for example, to build a buffer function y is equal to A, we need two inverters back to back. This shows the symbolic form, and this shows the transistor form. You might think that a non-inverting logic function could be built like this, in which the NMOS transistors are connected to VDD and the PMOS is connected to ground. But for electrical reasons best left to an electronics class, this is not allowed. This slide right here shows how to implement a NAND function. A NAND function takes exactly 4 transistors, 2 PMOS and 2 NMOS. You can verify these switch configurations here based on the inputs do implement the truth table for a NAND function. In the previous slide, we said that we could think of a NAND function as an AND gate followed by an inverter, but that's actually incorrect. A NAND function is directly implemented by 4 transistors as shown here. So how do we make a 2-input AND gate? It turns out that a 2-input AND gate is actually a 2-input NAND gate followed by an inverter. If we count the transistors, the 2-input NAND gate will take 4 transistors, while the inverter will take 2. So to make a 2-input AND function, it actually takes 6 CMOS transistors. This is why NAND gates are actually preferable to AND gates in CMOS technology, because they're going to end up taking less transistors, and they will be faster, because a NAND gate has only one level of logic to propagate through, while an AND gate has 2 levels of logic for signals to propagate through. So let's move away from individual gates and move towards combinational building blocks. A very important combinational building block is called a multiplexer, or a MUX for short. This is a symbol for a 2-to-1 MUX. Basically what you can think of this doing as steering either this signal or this signal to the output. If S is a 0, then this signal right here, I0, will be steered to the output Y. If S is a 1, then this signal right here, I1, will be steered to output Y. This right here is the gate level implementation for a 2-to-1 MUX. If we want to steer buses together, and here's some buses. This is a 4-bit bus and a 4-bit bus steering to a 4-bit bus output. All we do is we parallel 4 2-to-1 MUXes. Another important combinational building block is a binary full adder, which would take 2 inputs A and B plus a carry in and produce a sum output and a carry out. These are the equations for both sum and C out. Full adder is typically abbreviated as FA. We can use various combinations of full adder circuits to build binary adders that adds two n-bit numbers together. This particular adder right here is going to add two 4-bit numbers together. This particular configuration of full adder circuits is called a ripple carry adder, in which we simply use one full adder for each bit that we're adding, and the carry out of one full adder becomes the carry in of the next full adder. It's called a ripple adder because the carry sequentially ripples through these adders. This happens to be the slowest form of an adder, but it happens to use the fewest number of transistors. We're not going to care about how adders are internally implemented. We will simply use an adder symbol like this and say this building block right here will implement an addition of these two binary numbers. This slide shows a combinational building block known as an incrementer. An incrementer has an enable signal. If the enable signal is a 1, then the output will be the input plus 1. If the enable signal is 0, then the output will simply be the input. This shows one possible gate level implementation for an incrementer. Another important operation is a shift operation. A shift can either be a right shift or a left shift. A right shift can be thought of as a divide by 2, while a left shift can be thought of as a multiply by 2. Each of these show a shift by one position. For a right shift, D7 is going to move to the 6-bit position, D6 is going to move to the bit position number 5, and so forth. For the most significant bit, we're going to have an external input called shift in that will move and occupy this position. What happens to this bit in the right shift? It simply falls out the end and is lost. A left shift moves the opposite direction. Shift in data will occupy the least significant bit, while the most significant bit here will be shifted out and lost. This slide shows one possible implementation of a combinational right shifter that can shift to the right by one position or else passes input unchanged. It uses muxes to implement the combinational right shift for a 4-bit bus. The shifter has an enable signal. If enable is a 1, then the output Y is going to be the input shifted to the right by one position. The symbol right here is the right shift operation from the C programming language. If enable is equal to a 0, then Y, the output Y is equal to the input A. If we take this case here when enable is a 0, then looking at these muxes, A3 here is passed unchanged to Y3, A2 to Y2, A1 to Y1, and A0 to Y0. When our enable signal is a 1, then this input is selected, so the shift in input is going to end up shifting into the most significant bit position. A3 will go to the Y2 position, and so forth. Here our least significant bit, A0, on a right shift will be lost. It will not be passed to the output. We're going to finish up the discussion of combinational building blocks by discussing memories. A memory is a device that can either store data or implement logic functions. We're going to characterize a memory by two values. The first value is going to be K, and it's going to specify the number of locations in the memory. The next value is N, and it's going to specify the number of bits per location. In order to specify what memory location that we're accessing, we need an address bus. The address bus width is going to be log 2 of K. What that means is for an example, if we had a 16 by 8 memory, this is the number of locations the memory contains, so the address bus would be 4 bits wide. And it's going to contain the location that we're trying to actually access. For example, if this address bus contained a 0010, that's actually equal to 2. That means that we'd be trying to access location 2 in this memory. Recall this value N is the number of bits per location. So in this case, this example memory, we have 8 bits per location. So the output data bus would have 8 lines, 7 down to 0. Typically, in this class, we're going to view memory as containing data or computer instructions. In this example memory right here, 8 by 2, we have 3 bits for the address bus to specify one of 8 locations and 2 bits for our data bus, D1 and D0. If this is the memory contents, we'd say location 0 contained the value 00, location 1, 10, location 2 would contain 10 as well, and so forth. So we could consider these things as arbitrary 2-bit wide arbitrary data. Another way to view this, though, would be able to view these data bits as separate values that each implement a logic function, and we could actually implement two different logic functions in this memory. This f would be this logic function, and this G output would be this logic function. That is actually used in a technology called as field programmable gate arrays. But we're not going to view memories in that mode here. In this class, we're simply going to view them as simply containing data. So we would simply contain this as a 2-bit wide data, who in this particular example, location 7, would contain the data 3. In order to build a computer system, we need both combinational and sequential elements. This slide right here shows a very simple sequential element called a D flip-flop. A sequential element remembers a value. In this case, it's a 1-bit D flip-flop. The D, for example, by the way, stands for data. This particular D flip-flop is going to be rising edge triggered, which means that on the rising edge of this clock signal, we're going to sample this input value and transfer that to the memory state of this D flip-flop, which will then appear on the output Q. In this case, this input happens to be a 1 on the rising edge, so this 1 gets transferred to the internal memory state and then propagates to the output. So the Q output goes to a 1 when we clocked in this data input. A D flip-flop can have other inputs besides the D and clock. It can have something called asynchronous inputs. In this case, this flip-flop is shown with an asynchronous set and asynchronous reset. The bubbles on these inputs means that these signals are low true, which means that when they're in the high state as shown here, they're inactive. Here the reset line goes low, which means it's active. It's called an asynchronous reset because it does not pay attention to the clock signal. When this line is asserted low, we're going to force the internal state of the flip-flop to a 0, and thus the output will go to a 0. So at this point, this going low forces the output to a 0. Here, the set input is going to go low, and it's going to cause the internal state to go to a 1, which means our output will appear to a 1. One thing about these asynchronous inputs, they override the clock input. So even though we have a rising edge here and it appears that we're trying to clock in a 0, because this set is still asserted, I will keep this output as a 1. Our D flip-flop used the clock signal. Let's review some facts about clock signals. A clock signal is a repeating waveform that alternates between high and low. The time between any two rising edges or any two falling edges is going to be called the period, and then we're going to measure that in seconds. 1 over the period is going to be called the frequency, and we're going to measure that in hertz. We'll use various units in here to refer to both period and frequency. We'll use milliseconds to the -3, microseconds to the -6, and nanoseconds to the -9th. The corresponding frequencies are kilohertz, megahertz, and gigahertz. Typically, the high time is going to be equal to the low time, which means that that would be a 50% duty cycle. Duty cycle is defined as the ratio of the pulse width to the period. Let's begin talking about sequential building blocks. The sequential building blocks is going to be composed of combinational building blocks plus the flip-flops. The most common sequential building block we're going to encounter is a register. A D flip-flop by itself is not very useful because the D flip-flop, every active clock edge is going to get a new value. What we really need is a storage mechanism, is a storage device that we have better control over when it can actually get a new value. And we're going to call that a register. And this register is going to have an input called a load, here abbreviated as LD. And this register will only get a new value when the load line's a 1. If the load line's a 0, then it's simply going to remember its owed value. Let's see how we use muxes and D flip-flops to implement a register. Let's assume that load is a 0. And that means that this path right here, the 0 path to the mux, is active. But where is it coming from? It's coming from the output of the D flip-flop, which means that on every active clock edge that loads a 0, we're simply keeping the owed value of the register by loading it back into the D flip-flop. Now let's assume that loads a 1. What happens now? Well, that means that this path through the mux is active, and it means that whatever's out here in the D input is going to be loaded in to our register. This input also has a reset input. that's tied to the low true asynchronous reset. What we're going to use this is on power up. We'll keep this low for a couple of clock cycles, which just means that this register value will be initialized to 0. After a couple of clock cycles has passed, we'll set the reset back to 1, and then we'll begin normal operation of our register. Another very useful sequential building block is called a counter. When we just start discussing microcontrollers later in this course, we'll find that microcontrollers have lots of counters inside of them. A counter is simply a register with an extra input. The extra input is called increment, and when this is 1, then on the next active clock edge, the contents of this register will increment by 1. Let's see how this works with regards to this data path right here. So let's set increment equal to 1. So increment is equal to 1. This is an incrementer combinational building block. That means that whatever this Q value is, when you pass to the incrementer, it's going to be Q plus 1. This Q plus 1 will pass through here. We have load is going to be equal to a 0. So this guy through here is going to load, and we're going to, on the next rising clock edge, we're going to increment this current value by 1. In fact, as long as increment stays 1, on each rising clock edge, we'll keep incrementing the value in this register. If we want to load in the value, we'll simply put load equal to a 1. Load equal to a 1, we'll set this path active, and whatever D is going to be loaded directly into this register. Note that if load is both a 0 and increment is both a 0, what happens? If increment's a 0, this value right here, Q, simply passes through unchanged, so this is going to be Q right here. Load 0 means that this passes through here, so we'll simply load in our old value back into our register when both load is a 0 and increment is a 0. This concludes our review of digital systems. Next chapter, we're going to use these sequential and combinational building blocks to build a very simple computer. The computer will contain combinational logic, it will contain memory, it will contain a register, and it will contain a counter. So we will use all the elements that we've just discussed in this lecture.